Wonderful to be here, and I first want to thank all of you for hanging in here to the end. This has been a wonderful day and a half, but it's been a lot of information coming at you, and I think you've displayed both great energy efficiency and renewable energy in being here to the end. So thank you very, very much. Let me thank a couple other people. I really want to thank Jay Precourt for being the energy behind this meeting here at Vail, not just this year, but the past few years as well. Thank you to the Vail Valley Foundation and your support. Thank you, Secretary Schultz, for both your wisdom and your inspiration over the past day and a half. My Stanford colleagues, Lynn Orr, Sally Benson, Jim Sweeney, Jeff Ball, Jeremy Carl, a really strong team from Stanford. And let me thank one more person who has really been instrumental in putting this whole conference together, and that is, in fact, Carl Colby. Carl, brilliant work, and let's give him a round of applause. So we're going to hear from four experts, and let me just tell you who they are, and then I'll give you a sense about the topic. First is Stefan Heck, who is a consulting professor now at Stanford, but for many, many years was at McKinsey, where he ran the global clean tech practice, a very, very deep background in this area. Second, Dave Danielson. Dave is the Assistant Secretary of Energy for Energy Efficiency and Renewable Energy. That's the position I had under President Clinton. He was the Program Director at ARPA-E, which you've heard about before, the Advanced Research Project Administration for Energy. And he was in the venture capital world at General Catalyst. Theo Fleisch, formerly CTO, Chief Technology Officer at World GTL, and currently an advisor to Oberon Fuels. And last but not least, Denny, Executive Vice President of Volvo Group Truck Sales and Marketing for the Americas. Now, the title of this panel is New Technology Advances, kind of a broad topic. So we decided to narrow it down a little bit, and that is to look at transportation technology, an area that hasn't received a great deal of attention over the last day and a half, except for Dennis Vail from FedEx. And we're going to take two approaches to this. One is a top-down approach from Stefan and Arun. Stefan and Dave. You'll notice that Arun was on this panel, but we've made a switch. And a bottoms-up look with Theo and Dennis. Let me start with a few slides. This is my favorite triangle of how it is we need to work if we're going to get to a more sustainable energy future. We've really got to be working in all three areas. We're going to talk about technology, but obvious to all of you, what comes along with this, what also needs to be emphasized, is policy and finance. From yesterday's discussion of the rules around fracking to today's more than a few mentions of tax credits, policy looms large, and you're going to hear some of that today, even as we dig into technology. And obviously, policy turns into politics, as we heard at many points, including the fascinating data we got from Alan Murray on where the public stands on many of these issues. And that other aspect of the triangle is, of course, finance. You can't get any of this done without adequate capital. And it's got to be adequate capital all along the technology spectrum, from early stage R&D to later stage R&D to pilots to those initial commercialization projects to full-scale deployment. Different kinds of capital has to flow in, whether the technology is transportation, whether it's buildings, whether it's power generation, and across the whole range of fuels. One number that I love, whether I'm speaking to a policy community or a business community or students, and that is this number. $38 trillion in infrastructure is going to be required, according to the International Energy Agency, between now and 2035 to meet global energy demand. $38 trillion. Now, that's a big, big number. And this is independent of what, in particular, that infrastructure looks like, clean and less clean, the spread of technologies, but we're talking tens of trillions of dollars of investment, including a big chunk of that in transportation. And it's a terrific opportunity to both do well and do good. And I think that's what makes this area so very exciting. And finally, these are really the key technology strategies if you're talking about energy. Much of the last day and a half has been on the stationary side. Deploying cleaner electricity, modernizing the grid, as you just heard in that brilliant presentation from Arun, and obviously increasing efficiency in buildings and industry. But we're going to focus on transport. Alternative fuels, where are we in that? Electrifying the fleet, how far can we go with plug-in vehicles at this point and in the future? And of course, how do we increase vehicle fuel efficiency? Added to that, of course, is infrastructure, what information technology can bring to it, a whole host of things. But those are the key technology areas. What we're going to do now is take the next 30 minutes or so. We're going to hear from the four gentlemen on this stage. I'll follow up with a few questions, and then I hope we're going to have pretty serious time to take your questions and get into a conversation. So let's get started on the transportation front with Stefan. Now, Stefan recently wrote a book. He's not allowed to hold this up, but I am. It'll be out in a month. It's called Resource Revolution: How to Capture the Biggest Business Opportunity in a Century. This is an extraordinary book that he wrote with a colleague from McKinsey named Matt Rogers that really digs into this amazing opportunity we have going forward when it comes to clean energy technology and how to get it built and how to get it deployed all over the world. I will tell you one fun little thing that caught my eye. One of the diagrams is called Rise of Computing Power Compared to the Evolution of Animal Brains. And I guess computing just got to the point of humans, but we were back with the mouse, the guppy, the worm, and the bacterium not too many years ago. So we made good progress getting to the level of our own brains. Now, the overall focus of this book is resource productivity, but we've asked Stefan to drill down from there into the transportation area. So with that, take it away, Stefan.
Thank you, Dan. I'm going to take you on a 6-minute journey through time, and I'll pick up where Arun left off, which is to remind you how much of the automotive technology that we have actually was magic once upon a time. I want you to go back to the world of your great-grandparents, their childhood, right around 1900 probably for many of you, and to imagine back in that time. They were just getting electrified lights, just getting indoor plumbing. There were no cars yet. And they had just gone through the biggest transportation revolution that the world had seen up until that time. And by the way, I'm going to focus on cars because you're going to hear more about trucks from my colleagues on the panel here later. And that revolution was the invention of the railroad. Before that time, to move people or to move cargo was incredibly expensive. And really, all the cities were on seaports because that was the only efficient way to move cargo, to be on a river or be in a seaport. If you try to move stuff over land by wagon, it was 25 cents a ton mile, and it basically meant the trade only happened near cities within about 50 miles or so. And most people in that era, unless they were pilgrims who emigrated to America or pioneers who settled the West, they would have grown up, lived, and died in the space of 100 miles and would have never gone beyond that. And then your great-grandparents witnessed not only the Transcontinental Railroad and the drop of the cost of that same ton mile to less than a cent, 0.8 cents per mile, but then witnessed the internal combustion engine. Most people don't realize the internal combustion engine actually was invented in the 1840s, and then it took 30 years to get a model that didn't blow up after a few minutes of operation. And then it took another 20 years to embed that engine into a vehicle. The first one actually was a bicycle. There's some very funny pictures of the first auto bicycle that was created. And it took another 20 years for it to actually be deployed into the kinds of vehicles that we know. There were 600 car companies in the US alone in 1911. Most of those have died and faded because people tried all different kinds of designs before they standardized on what we know today. You typically had about 20 horsepowers, and you typically went no more than 20 miles per hour. There are also regulatory barriers. One of the funniest stories I found was that in many cities, a flagman was required to walk ahead of every single internal combustion car to warn pedestrians, because cars were very unpredictable compared to horse-drawn carriages, where you kind of could tell where they were going based on where the horses were going. So that was a regulatory barrier to going faster, obviously, than the speed that a man could walk ahead of the vehicle. The other funny story is that New York convened a conference right around that time, turn of the century, to solve the biggest environmental problem of its time, which was not the automobile, but it was the fact that horse manure was piling up at every street corner, and there were projections that New York would be piled in 4 yards of horse shit by the end of the next decade. Obviously, that has not come to pass, and the automobile was the great environmental savior, at least of that decade. I'm going to turn now to today, and why am I as optimistic that that same level of dramatic productivity increase and decrease in the cost of transport, and therefore decrease in the basic element of how trade in our economy works, is ready to happen again. Let's talk about you all. Show of hands, how many of you own a car? Good, almost everybody. Keep your hands up if you like your car and you really chose well. Most of you, good. And now, show of hands, how many of you think that you make good use of your car, it was a good investment? Still most of you. All right, I'll give you a statistic. The average utilization of your cars in America is 4%. And by the way, not only is your car lonely most of the time, because it's not with you 96% of the time, but it also sees you as a really upset, angry driver, half of that 4%, because you're either looking for parking or stuck in congestion. So your real productive use out of the car is about 2% of the total time that the car could drive. Look at the same thing on the fuel side. We burn about 1% of the fuel to really move the driver, and it's 1.6 on average for the US, plus whatever portion of the passenger, so 1.6 in total, from A to B. Most of it gets turned into heat, which we use occasionally when we're in places like this where it's cold outside, and we use that for heating the passengers. Most of the time that heat goes to waste. It's friction, it's aerodynamics, and it's moving the car itself around. So we've already heard that lightweighting is one lever to improve efficiency, because that would reduce that element. Braking, regenerative braking that you have in electric cars is another lever to do that. So 1% of the fuel and 2% of the cars. And then to add the third element, how much of the roads do we use? It turns out to be 0.1%, because most roads are only really anywhere near full capacity in one direction 5 times a week during rush hour. And even then, sometimes we get beyond 1,900 cars per lane per hour, and that's what we call a traffic jam. So throughput actually drops if we exceed that number. And the rest of the time, we have to preserve very large spacing because we want to avoid accidents. We humans are actually pretty terrible drivers, and while we have professional pilots and professional sea captains that get licensed and use autopilots, we don't do the same thing to the same degree for vehicles. Now, let's talk about the future. That's the productivity opportunity, right? If we could take our car utilization from 2% to, say, 50%, which is already not very efficient, but decent. That's sort of what we do in IT, or many industrial assets or utility power plants are actually right about that level in many parts of the world. If we could take it from 1% of the fuel that's used to move the car to what an electric drive can do, which is typically, when you look at the system efficiency, probably 60-70%. Again, you have to change the aerodynamics and the tire friction as well. And then what if we could up the usage of our roads to actually space cars more closely together? Volvo and a bunch of Japanese companies have been doing some very interesting work on convoying and the aerodynamic efficiency you gain, but also the spacing efficiency you gain by basically allowing cars to move together. What that really is the beginning of new materials and information technology coming into vehicles and disrupting the very basis of the technology that we had. So the same way that the internal combustion engine was disruptive and gasoline was disruptive, we now have information technology come in. Some of you may have tried the Teslas that are sitting outside. They are now upgradable by phone, the same way that your iPhone is, right? They download the latest software, they get new features, they also report back what's wrong. They hardly need to be maintained because they have very few moving parts. It's an electric motor, and then there's no transmission, there's no oil changes or any of the usual things that you would do for a car. But how can we go beyond that electric efficiency? Well, it's sharing. It's already very popular on the West Coast, where some of us live. People actually just order a car when they need one, and they don't need to own it anymore. And you do get utilizations that are 50-60%. The last element is that the government is now considering a vehicle-to-vehicle communication standards for 2017. Why is that important? If I have vehicle-to-vehicle communications, the cars can talk to each other. That is the 21st century equivalent of the flagman warning everybody that there's a car coming, because now the vehicles can actually coordinate. You can imagine, instead of having a carpool lane, we have an automatic vehicle lane where the spacing can be much, much closer, and yet you can move at densities that are like a traffic jam, but you could be going 60, 70 miles an hour. Even more so, your great-grandparents did not know stop signs or street lights. We developed those basically to avoid collisions at intersections. If we had that level of IT that we have in our iPhones and in our laptops in our cars to communicate with each other, we would not need stop lights or street signs, because the cars would automatically coordinate to zip through the intersections. So again, most of the fuel inefficiency from the stop and go would suddenly be eliminated. And you may think that that's sort of a utopian vision of the future, but the timeline for car companies to have electric cars, you've already seen them on the road. The BMW i3 that's coming out is basically already applied carbon fiber technology, so instead of being $80,000 like the Tesla, it's a $40,000 car with similar range and similar economics. We're going through a battery evolution that Dave will talk more about that basically takes us out by the end of this decade to about $200 per kilowatt hour, maybe even below that, down from about $400 or $500 per kilowatt hour. Why does that matter? That means double the range, half the cost. The battery is the most expensive component. If I share those cars, I can amortize that car across a much larger number of people. And if you think about the 4% to 50%, that's that same tenfold increase in productivity and therefore a tenfold decrease in the cost of what it really costs me to drive my car for a certain distance. So suddenly everybody can afford cars in bits and pieces. The other thing you have to think about is you may want a small car for your daily commute, but you want a big SUV for your trip up to the mountains. If you're sharing the cars and you can just order up whichever one you want at that moment, there's seamless efficiency. You're not driving around the 7 seats behind you when you're only driving somewhere by yourself. So I'll turn it over to Dave for how's all this going to happen from the technology point of view.
So we're going to make a jump from Silicon Valley to Washington, D.C., and Dave runs one of the largest clean energy R&D organizations in the world, budget around $2 billion now, up from $1 billion when I was there. And big focus of that is on transportation. So take it away, Dave.
Well, thanks, Dan. You left very big shoes to fill. I'll do my best, filling in as the former Assistant Secretary yourself. So I think one thing I love about this conference is it seems very focused on outcomes, national outcomes. And so I think the top line framing for me here is, what do we want to achieve in terms of the transportation sector? Energy security, we want affordability so that we can have a strong economy, and then we got to deal with the climate. So I think that's the big frame, right? And so I think there are four kind of interesting cross-cutting things to think about up front, and then I'll dive into some of the technologies that I think are going to drive us forward. The first is, yesterday we learned all about the shale oil, tight oil boom, to the point where we are looking likely to be at zero net imports within the next 10, 15 years. But one thing I wanted to remind, which is a phenomenal thing, it's so good for the country, but one thing I want to remind folks is that we still are part of a global oil market. And so I think that a position of strength for us, I think, will really be if American consumers and businesses have choice, right? If you have a vehicle that you can fuel it up with gasoline or electricity, fuel it up with natural gas or gasoline, that if, as we learned again yesterday, that the event-driven, geopolitics-driven oil markets, when they do what they do, we need to have the ability to make decisions. If someone wants to raise our gas prices to $5 a gallon, we can go make a decision to use a little bit more $1 a gallon electricity or $2 a gallon natural gas. So that optionality is something I think we need to keep in mind beyond just being a not a net oil importer. Another area that I wanted to touch upon is climate. Right, so we've talked a lot about oil production and the strength we have there, but most scientists, the UN, IPCC, we got to get down to about 80% of where we were in 2005 by 2050. So there's a lot of work to do, a lot of technology we need to develop to get there. I want to remind people that we've got to look at advanced technologies to get to that kind of goal. And so I wanted to talk also about inertia. every year Americans buy about 15 million new vehicles. And so if some new technology was 100% of new sales, it wouldn't be 100% penetrated for 15 to 20 years. And most technologies take 15 to 20 years to go from initial introduction to even being in almost all of new cars. So we're looking at kind of a 30, 35-year transition. And so anything we want to see happen in 2050 has got to be underway now in 2015. So I think as the Secretary told us, we got to get to work now. We got to be moving now. And so the frame I wanted to put on this, I think, let's say we got to get down about 80%. In a simple way of thinking, you could say, okay, we got to double our efficiency, and we got to go to fuels that are half the carbon intensity. Roughly speaking, there's a lot of room for movement in there. I think the revolution in the last few years has been the President Obama and his administration dramatically increasing fuel economy standards, the CAFE standards. From 2010, where for 30 years we had been at about 20 miles per gallon average fuel economy, with the goal now to get up to more than 50 miles per gallon by 2025. So that's a big frame. If we can achieve those goals, we have doubled our fuel economy. And so essentially that's going from about 2025 to about 50. That's a 100% increase in efficiency. So how are we going to provide for that 100%? What are our options? And so the first one I would point out is we have a ton of headroom in combustion. Combustion research we still have a ton of opportunity to improve there. And our estimates are that over the next 15 to 20 years, that we can improve combustion efficiency in engines about 35 to 50%. So that's a big chunk. Lightweighting of vehicles, as Stefan mentioned, is a big deal. The holy grail for us is a vision where you could have a car where every steel component was replaced by high-performance plastics, carbon fiber composites, that would be about the same cost and have the same strength. Right now, they're more expensive than that, and we're getting to work on that on the R&D front. But if we could achieve that big, hairy goal of all carbon fiber composite as a thought experiment car, we would be able to lower the weight by 60%, and that would give us 40% of that 100% we need in fuel economy just from lightweighting alone. But what we're seeing the industry do now already is they're adopting technologies like hybridization, start-stop. That's getting them about 25%. Technologies that are kind of already on the shelf. But they're also deploying things like high-strength steel. We heard about aluminum. We're going after magnesium going forward. These are technologies we've been working on, public-private partnerships with the government and the industry for a while, and they're now getting into the market. Then there's the next area to turn to, I think, is electrification, plug-in electric vehicles, which are going to be part of the orchestra of opportunity here. For me, what I get excited about with electric vehicles, domestically produced fuel, electricity, and if you look at the added efficiency of an electric vehicle over a combustion-oriented vehile, you're looking at the equivalent of $1 a gallon of fuel cost if you do an equivalency to gasoline. So there's a tremendous fuel savings, but you know what? These cars are still expensive, and it's really about the battery, as Stefan mentioned. But we're doing a lot better than most people are aware of. I want to let you know. Most of the projections I see are not quite on. They're not where I think they should be. Right now, we're at about $400 per kilowatt hour. So that's the amount of money you'd pay for a kilowatt hour of a battery. Our analysis says if you wanted a simple 5-year payback for a Nissan Leaf, 100 miles, you need a battery at about $300 per kilowatt hour. If you want your Chevy Volt to have a 5-year payback, that's about $200 per kilowatt hour. And if you want a much stripped down economy version of a Tesla Roadster or Model S, 300 miles to pay back in 5 years, you need to get down to 100. And so we're at 400. We've got technology at Argonne National Labs and being developed by the private sector on the shelf in prototypes with twice the energy density of the materials today, which would take us down to about $200 per kilowatt hour just with that one innovation. And so I'm very confident towards the end of this decade, we're going to be close to that 150, 125 kind of goal, at which I think we're going to see a lot of penetration of cost-effective electric vehicles. Sales doubled last year. In the next 2 years, we expect sales of electric vehicles to rise to the 1% of new sales level, which I think will be a big moment for that industry. We're also working on fuel cells. For the long term, I think we need to keep the optionality of very low carbon hydrogen fuels powering fuel cell vehicles that would allow you for fast refueling, the kind of range that people would expect, and the kind of performance people would expect. We've had dramatic reductions in cost over the last 10 years, 80% reduction. We're seeing some early market introduction in Southern California in the next 5 years or so, getting some of these technologies actually out in the field. But I think that it's going to be a little while before those technologies reach cost competitiveness. I want to briefly touch upon the other side, low carbon fuels. And so my office invests in technology for domestically produced low carbon biofuels. And starting with under the Bush administration, the second Bush administration, there was a major push to achieve cost-competitive cellulosic ethanol. This is ethanol that's made not from food, but from non-food crops that are on land where you likely couldn't grow food. And so you don't run into the food for fuel debate, and they have dramatically lower greenhouse gas emissions, 50 to 80% below standard gasoline-powered fuel. Our estimates are that by 2030, the United States could produce about 1 billion tons of sustainable non-food biomass. And that would, if we converted all of that into biofuels, that would cover about 1/3 of our current biofuels usage. So it's an important component, but again, none of these technologies get the job done on their own. Cellulosic ethanol is only a good replacement for gasoline in the fuel pool. Since in the last couple of years, we've achieved, basically gotten the technology to pioneering commercial scale, and in the lab at pilot scale, we've achieved the technology breakthroughs required to get to about $2 per gallon cellulosic ethanol. Now we're letting the industry really scale that up. But now we're turning our eyes to an exciting new horizon for biofuels, direct drop-in hydrocarbon biofuels that could replace the whole barrel of oil, gasoline, diesel, Jet A, chemicals. And so we're looking at exciting new approaches to synthetic biology to convert sugars into hydrocarbons. And we're also taking a book out of the oil and gas industry and taking catalytic cracking technology to convert biomass directly into hydrocarbons that can be refined in an existing oil refinery. So we see a lot of opportunity there. I think we see that towards the end of this decade, we think we'll have proven out the technology, and then it'll be a matter of scaling the technology over the decade after that. We're also invested in LNG and CNG, which you're going to hear more about some of the opportunities related to natural gas as a fuel. We're also investing in a number of pathways that Secretary Schultz mentioned of producing hydrogen from renewable sources directly from solar electricity using electrolysis or biological methods. And so I think that gives you a reasonable kind of a lay of the land of the kind of things that we're investing in, and I look forward to continuing discussion on this topic.
Thank you, Dave. Dave, I think I like the phrase, an orchestra of opportunities, and that's kind of the first half of this, a top-down look. Now we're going to take a look at one instrument in the orchestra, and that is DME, and its use as a fuel, a very interesting fuel in the world of trucks. So we'll first hear from Theo, and then we'll move on to Denny, and then we will start to take your questions.
Thank you very much, Dan. I would just like to thank the organizers for inviting me. It's a true pleasure to be here at this Global Energy Forum. And I thought I would add some additional flavor to the word global by using my best German accent. So, anyhow, in the 90s, I was leading the alternative fuel division in Amoco in Chicago. We looked at dozens of new alternatives that could be beneficial over the traditional gasoline and diesel. And actually, the most promising fuel we found was DME. And hopefully, after you have heard Danny, you will agree that this could be a potential game changer for diesel engines and be a fuel that we produce in North America. So what is DME? Multi-source, multi-application, ultra-low emission fuel. It's a very simple product, a little bit of chemistry. 2 yellow carbon atoms are connected with a blue oxygen. That's very rare. Only about half a dozen of molecules don't have carbon-carbon bonds in the millions of organic molecules you have. That explains the different combustion that we have, sootless combustion in diesel. You have heard from Secretary Schultz talk about the Montreal Protocol, where chlorofluorocarbons were banned to protect the ozone layer. What was the replacement for chlorofluorocarbons? Propane and DME. So there's a good chance that you have been in close contact with DME over the last 60 years by using a consumer product such as hairspray or shaving cream. So it's known and used for 60 years. There are cost-effective, well-known ways of making it from natural gas, shale gas, flared gas, biogas, waste, and so on and so forth, and I'll tell you more about it. It handles like LPG, So we can use the well-known existing LPG infrastructure to distribute DME to the customer. In China, 40 million barrels of DME are used for cooking. 40 million barrels of year are used for cooking. But today, we will focus on this most exciting application, which is the diesel market. So the invention and early work was done in the early 90s. We worked with Nevis at the time, and we did the early work at the world's largest engine testing lab in Graz, in Austria. And we got immediate superlatives coming back. Wow, the ideal fuel, the Wunderbrennstoff, the wonderful. We have never seen something like this. Well, hopefully you will see some of the excitement from Danny. There has been a 20-year effort going on, but up till now, no commercial DME vehicles are available, but that's going to change in the next 2 years. We coined the term the gas refinery at Amoco about 15 years ago. This is a very simplified diagram here, but it shows that technologies exist where you can take natural gas or biogas, you go through a reforming process, and then you can make the products that you see up there. You can make conventional fuels. You can convert natural gas into gasoline. You can convert natural gas into diesel, being done by Shell and Sasol down in Qatar. You can also convert them into alternative fuels, such as DME. Hydrogen would be made this way, butanol and others. Also, the same process is being used to make some of the more important chemicals, such as methanol, fertilizer, olefins, and plastics. Now, because of the high gas price in the past, nothing of this was done in the United States. But today, because of the abundant low-cost shale gas reserves, there are lots of activities. The arbitrage between gas at about $25 per barrel and the product being worth $100 obviously is a strong financial incentive to do those technologies. So there are projects in all areas. You will see over the next 5 years, hundreds of billions of money invested, and we will become a major producer of methanol, fertilizer, and some of the other products here. Why are we now at the brink of seeing DME become the diesel alternative? It's because of a company called Oberon Fuels, based in San Diego, led by the president, Rebecca Boudreau, who is in the audience. Where are you? Right over there. What they have done is the following. Rather than building a very large-scale plant, they have developed a small-scale plant where they can make as little as 10,000 gallons per day, which is enough to fuel about 100 trucks. It's this small-scale application that breaks the chicken and egg syndrome as to what do we do first, large-scale DME, 100,000 of trucks. So they have this model of a centrally placed DME facility. More importantly, they are also focusing on biofuels. When you are in California and you see all the biogas available from cow manure, that explains the little happy cow there, or from waste materials, many of those plants can be built using waste biogas. So now you have a renewable biofuel. They also have done all the work to get approval for DME, going through that process. And most importantly, they have formed this partnership with Volvo to make DME engines available. And the first DME is being produced in Southern California. So the stars are aligned, finally, to make this happen in North America.
So Denny, I don't know whether you're a trumpet or a violin, but you're one or the other, so please take it away and let's hear from you.
Well, first of all, let me just say that I want to get to questions very quickly, but I do want to talk a little bit about Volvo, a little bit about trucks, and then I'll finish with natural gas and DME. First of all, Volvo, second leading manufacturer of heavy-duty diesel trucks in the world. We also are a leader in making heavy-duty diesel engines, and we are, out of the 187 or 200 countries in the world, we're in 180 of them. Very global company, adhering to all of the local demands in terms of emission controls. The company is very much part of our core values is care for the environment. Been there for 40 years before it was fashionable. So about a year and a half ago, we looked at the conundrum of different options coming at us from a fueling standpoint. And we decided on what we call the blue power strategy, which essentially embraced certainly the clean diesel that we're burning today, but also natural gas. And we were looking for perhaps an answer that not only gave us a diesel-like performance in our trucks, but also had the advantage of some renewable, sustainable fuel options. And we think that will be an important part of the future. So that's Volvo, a large part of the players, certainly one of the big four here in North America and South America. Let's talk about trucks a little bit. First of all, we pull about 80,000 pounds along those 18-wheelers that you see on the truck. Recent studies say that we move about 80% of the goods in America. We like to say in trucking, if you bought it, we brought it. With all the discussion of rail and other means of transportation, the studies show in 10 years we will still move 80% of the goods. So the trucks are going to be around us for a long time. The things that are important about trucks: we burn about 21,000 gallons of fuel a year, travel on average about 120,000 miles per year. So we're big consumers. What are we doing to obviously address the emissions consequences of that? We're looking at everything from aerodynamics, better engines, more efficient engines, weight, materials, and we're very much interested in, as I said, what has been emerging into the natural gas and DME area. So let's just talk about natural gas a little bit. I cannot sit down for more than 10 minutes with any of our customers without addressing this natural gas. Tremendous amount of, let's call it, noise in the marketplace. It's been there for 3 or 4 years. Today, natural gas trucks sold in America are 2% of the market. Last year, officially, 2013, just over 4,000 new trucks were sold as natural gas. And I want to be clear, we're not anti-natural gas. We were one of the market leaders out of that 4,000. And I also have responsibility for Mack Truck. So one of the ideal applications for natural gas is in refuse. Refuse, you come home every night, you can slow fill the compressed natural gas, you can send it out and with multiple stops, come back and do ideal application. You're local, you have your own filling station, and you send the trucks back out the next morning. As you get more regional and more, certainly when we get into long haul, natural gas, as Dennis pointed out yesterday, starts throwing up several obstacles to get over. You have the question of infrastructure. How many fueling stations can you find? If you're out there with a natural gas truck, you got to feel sure. And trucking companies, more than Dennis, but all trucking companies rely on certainty. So they want the infrastructure to be there. There's also big questions of marks around the efficiency. Spark-ignited engines that dominate what's sold today are not as efficient as diesel. They're 15 to 20% less efficient. You have residual value concerns. You have infrastructure concerns from our dealers, our 560 locations out there. An estimate to, as I think Dennis mentioned, an estimate to upgrade one bay to fix a natural gas vehicle is over $200,000. All these are being worked on. A lot of people are spending a lot of money to overcome all the obstacles. But I mentioned the DME, the real attractive thing from DME from the standpoint of what we do is it more closely replicates the attributes of diesel. It burns almost as efficient as diesel. It requires, as this slide shows, it requires very little. It's still the base diesel engine, so we have to have different injectors and fuel pumps. So you can't go one day and fill up with diesel and then drive down the road 500 miles and fill up with DME. But it's a very small sort of technology leap from diesel to DME. The other thing is one of the big drawbacks with natural gas is the amount of tank. And they're working on this. They're trying to make them more compact, et cetera. But as Dennis mentioned, LNG needs cryogenic tanks, which are heavy, et cetera. And you need approximately, with LNG, you need twice the amount of tank space. And with CNG, you need 4 times the amount of tank space as you do with a diesel. So this takes up valuable space on the truck, whether it's on the rail or behind the cab. And for example, you see the aerodynamics of a 18-wheeler there. Keeping in mind the best way to conserve greenhouse gases is not to burn them. If we create too much of a gap between the trailer and the tractor, it creates a degradation of fuel efficiency. So with DME, there's no DPF, so it allows more rail space. DME does, again, need twice the tank space as diesel, but DME, because it travels in a low-pressure environment, you don't need, you can just, the tank can be a simple, like a propane-like tank, so they're the same weight, et cetera, and in terms of rail space, we can work with that a little easier. Finally, again, those of you that heard Dennis speak yesterday, he talked about the hurdles. And the reason why we think, as this DME fuel option matures, you get some of those major hurdles will be overcome. The driver will like it because it's the same engine power. You get the same torque and power with DME as you would diesel. There's also no special handling of equipment to refill the tank. Today, an LNG driver is supposed to have the face shield, special gloves, and he's working with a cryogenic fuel coming through. You can actually see the frost on the fueling lines. Technicians, if there's a leak in your shop for DME, it pulls down, so it's heavier than air and it pulls. So you don't need the same restrictions as if gas escaped in that same maintenance pool. The shop manager likes it because there's no upgrades, as I said, so you don't have to manage with the fire marshal all of the same things you would with gas. And the decision maker, again, as Dennis pointed out yesterday, one of the big capital hurdles you have with natural gas is the capital. The tanks themselves are $65,000. So with simpler tanks, and not as much investment in terms of fulfilling stations. So instead of $2 million, you're looking at about $125,000 or less to install a DME filling station. So these are the things that some of the dynamics that worked into Volvo's partnership with Oberon to lift this DME notion off the launch pad. Thank you.
Good, thank you. And thanks to all 4 of our panelists. Let's jump right into questions. We've got about 17 or 18 minutes. And let me start with Dave. So you're sitting in a big office in Washington with a big budget, some policy reach, and you find all sorts of interesting fuels out there. We just heard about one of them. There's natural gas, there's biofuels, there's diesel. How do you sort through that as someone who's got to decide where to put taxpayer dollars, has got to decide where to put your policy emphasis? We have an abundance of opportunities. What do you do sitting in an office in Washington?
Yeah, well, that's a great question. There are all these options, and you do have to map out which sectors are most appropriate for which types of technologies, as was discussed. Whereas in light-duty vehicles, fuel efficiency and combustion, lightweighting, electrification are going to be major strategies. Whereas when we're looking at things like heavy-duty trucks, it's not likely to be an electric vehicle, an all-electric vehicle, right? So you have to look at, I think in the long run, you've got to look at things like low-carbon liquid fuels, much more efficient combustion and conversion, those kind of things. So, really analyzing it by sector is very important. But one thing I'll point out to y'all is that, so I'm a co-chair of the U.S. Drive Partnership. It's me and the CTOs of the big the 3 U.S. automotive companies. We've got fuel providers, we've got utilities. And I think we're continuing to suffer from a good coordinated set of activities or policies around building out vehicles, infrastructure, and fuels. And it's really, I come from the private sector. I believe in the power of the free market, but I'm becoming more and more convinced that the free market alone, without some sort of public-private partnerships and planning, we're not going to be able to build out the right infrastructure in the right way. I think the chicken egg problem is very difficult. You'd hear from the automakers, hey, I built a bunch of E85 compatible vehicles, but then no one built the infrastructure, right? And then the fuel folks are saying, well, hey, I've done my work, you do your work. So I think we need to all bring, kind of like we saw yesterday around the concept of the gas flaring regulation, bring people together to develop a common vision, a common roadmap for how we can incrementally build out infrastructure in an appropriate way with the private sector right there, but with the government kind of helping to build it out.
Good. Stefan, 2 questions for you. I'm just going to try to put these together so we're very efficient. Cars are parked 95% of the time. Why not use them for storage, for electricity storage? Doesn't that make good sense?
Absolutely. I think on multiple dimensions, actually. One is the used car batteries that have slowly diminished in capacity, you can actually then use as stationary storage. The second is you can use the cars even just as they're plugged in and charging generally to do frequency regulation, very short-term balancing of the grid, which is a very important function you saw in Arun's slides earlier.
Just to be clear, I may have not made this clear. We're talking about plug-in vehicles at this point.
Yeah.
Good.
Yeah. So again, you can either use them after they're done in the vehicles and they're lower capacity, but they still work. You could put that together with your solar array at your house or in an industrial installation, or you can do it very short term. And then the third is, if you really get full control over the charging, and you can begin to do the kind of IT integration of the grid so that you know when at that forecast period at the finer granularity, you can actually use large numbers of cars to even meet large upswings in demand. So that the Cal ISO curve that you saw, that duck shape, the electric vehicles, once you've come home from work and you plugged it in and you're now in the house, they could contribute to actually managing that ramp. For that third application, we're going to need very large numbers so that you don't kill any one particular car's battery, of course.
So switching vehicles, what about autonomous vehicles? How long until we have fully autonomous taxis, for example? And how are the trials going?
Yeah. Well, first of all, autonomy is sort of a continuum of technologies. A lot of it is already out there. If you've seen any of the high-end Mercedes cars that do lane following automatically or that warn you for proximity and apply the brakes automatically, Volvo has similar technology when you're about to hit something or hit the car in front of you. You have the self-parking technologies that allow you to back into a space. There's now a trial for doing the same thing over your phone so that your car can self-park without you in it and therefore fit into tighter spaces. So those are all component pieces that are already out there in different vehicles, obviously still mostly at the luxury end. Then you have the Google cars. The challenge with the Google cars is they work. They've driven hundreds of thousands of miles with very, very good safety record. That technology is still fairly expensive. It's about $80,000 to upgrade the car with the LiDAR sensors. But that learning curve, which is the rate of reduction of the cost of the technology with every cumulative doubling of capacity, it is steeper than Moore's Law and it is steeper than solar. And those have been sort of our paragons of technologies that are coming down very rapidly in cost.
Good.
So
Very quick, go ahead.
just to get to a number, there are a number of car companies that have committed to having their first vehicles out 2017. And the sensor technology is dropping such that by the end of the decade, I think the technology will be affordable. The question is really, will our regulation keep up? And how will we deal with all the liability and consumer adoption issues of letting go of your vehicle when you are on the road?
Dan, a real quick comment that I think this is the kind of disruptive innovation that we're going to see out of the ARPA-E program at the Department of Energy as well. This was on no one's mind before DARPA put out a grand challenge about self-driving vehicles that a bunch of students at Carnegie Mellon and elsewhere got after. The first year, none of them worked. They all ran into stuff like 3 feet in. The next year, someone actually achieved it. Then quickly, Google took it to another level, and now automakers are talking about putting it in 2017. So I think that's the kind of technology optimism I think that we should make sure that we realize is a reality going forward.
10 seconds on this. Driverless delivery vehicles going over established routes.
Absolutely.
Okay.
It's even easier to do because you got a known route.
Good. Denny and Theo, two things. How about burning hydrogen in IC engines or hydrogen in a hydrogen fuel cell? Secondly, why not use natural gas directly in internal combustion engines? No need for DME. Obviously, there's a passenger vehicle truck distinction, but
You take the hydrogen.
Yeah, obviously people have looked at hydrogen for a long time. We were supposed to be a hydrogen economy, and especially in California. But people don't realize when they say hydrogen is the most prominent molecule or element in the universe or here on Earth. Yes, it is, but it's all water. It's the end product of combustion. It's like talking about CO2 as the source of carbon. There are some thermodynamic laws that make it very difficult to take your end product of combustion, water, and have now an efficient process to go to hydrogen. That's one thing. The other one is hydrogen is a nasty molecule. It's small, it likes to diffuse through metals, it's difficult to handle, very low energy density. You have the same issues as with natural gas, compressing it or liquefying it to get enough energy density. We are spoiled. Diesel and gasoline are customer-friendly fuels, easy to refill, going 600 miles. We are spoiled. If you want to have a hydrogen car, good luck. You fill it up twice a day. So it's the manufacture of hydrogen and the use that is very, very difficult.
Yeah, we do obviously have customers today that are using CNG and LNG fuels, but it's being used through a spark-ignited process. Diesel ignites on combustion, DME ignites on combustion, which is much more efficient than spark-ignited engines. So it's happening today. The CNG infrastructure is building out organically, very aggressively. LNG is stumbling. If you've read some of the trials and tribulations of the people that are trying to get that infrastructure going, it's a huge chicken and egg problem. But from the standpoint of the diesel engine or of the engine, and I will say on Volvo, we don't really care that much what we're burning in our engine. We would certainly prefer scale so we can make it all economically work.
go ahead, please.
Just a quick comment on hydrogen. You know that natural gas being a tremendous bridge fuel for decades. You know, to continue to increase our energy security and lower the carbon footprint from our transportation sector. But as we get out into that longer range, if we are going to have to get down to kind of 80% reductions in GHGs from the transportation sector or lower, you know, one credible pathway for natural gas could be centralized steam methane reforming to make hydrogen and do CCS, you know, store the CO2 underground and then distribute the energy as hydrogen. I'm not saying it's going to be easy, but there aren't many other pathways you can envision to take advantage of methane in the transportation sector in the long term with very low greenhouse gas emissions.
Dave, will you keep going, please? Tough question. Why is DOE focusing on biofuels? We don't need biofuels as a major energy source, and it's not better for the environment.
I do not accept the premise of the question first. I had media training. I was taught about that.
Go, Dave.
Well, so the first thing I would say is that I think we want to be outcome focused, right? We shouldn't get emotionally attached to feedstocks or conversion devices, right? They're not human. We don't need to be emotionally attached to them. But I think if you look at, so what we should have is a low carbon domestically produced fuels effort, which we have, right? And I see that the biofuels are an important part of that, cellulosic biofuels, in that you do, because of the carbon dioxide reuptake you get with biomass, you get very low life cycle greenhouse gas emissions from cellulosic biofuels. And so, as it relates to options, this is a very low carbon option that can very likely provide hydrocarbons, which will give us the same kind of performance that we really are going to want, the kind of performance we're getting today. So I think biofuels, we have a tremendous amount of work on sustainability. And we are very careful about that, especially as it relates to food production or other environmental impacts associated with farming and biomass. And so I absolutely consider, again, it'll scale to about a third of all of what we're using today. It's not the only, it's not going to be a silver bullet kind of technology, but I think it's going to be an important part of the orchestra.
A third of the biofuels we're using today?
No, a third of all of the petroleum we use today could be displaced by 1 billion tons of biomass converted into fuels or chemicals.
And to be clear, you're talking about cellulosic feedstocks.
Right. Cellulosic.
As opposed to what we do today, which is the starch in a kernel of corn.
Exactly.
Okay.
The other thing I would add to that one, Dan, is ultimately we need to find a way to get aircraft to decarbonize, and that cannot be electrified. And I would be very skeptical of flying in a compressed natural gas airplane myself as well. So.
All right. Important question. Infrastructure challenges for broader use of DME. Let's be quick about these so we can get to a few others.
I'll be quick. And the advantage of DME as opposed to, say, LNG with the cost per fueling station and that whole chicken and egg, the DME basically handles transports much like propane. So the infrastructure to develop it, the initial, if you wanted to build your own station, it's less costly. And you have the advantage of it being a low cost and already sorted with the pressure, the transportation part of it is all much easier than LNG in the case, if you want to compare it to that. We also have Oberon's developing the small scale skid-mounted type of operations that can be put locally and convert wasted flared gas or other type of small-scale type of activity. So we've got a couple of things that could ramp us up quickly.
Good. Interesting question. Anybody can take it. Is there an opportunity for hybrid trucks, given experimental, high-efficient, lightweight electric motors and new batteries, and the potential for charging going downhill?
I'll start out because I'll say 3 or 4 years ago, we were working very, very hard on electromobility on the things like refuse applications, where there's a lot of stop and go distribution in cities where you can capture the braking energy. That, I got to say, was hijacked by natural gas. I mean, we had trucks on the road in New York City that basically died to death because of the rush toward natural gas in that area.
So it was not a
as someone said,
failure of technology.
It was really the appeal of natural gas from an economic standpoint. And as someone said, long haul is not really a great application for electromobility.
But I think the technical potential is there. The best evidence is that you can see rail converting to hybrid diesel-electric engines.
Speak about that for a second.
Well, the newer engines, basically, the diesel isn't used to actually directly power the wheels of the train, but is first converted to electricity that then powers electric motors, because then you get the same benefits.
Including with braking, regenerative.
Braking you don't get because there's no grid or place to put it back into. An electrified rail is already regenerating today, but you'd have to electrify the tracks to build it.
And I wanted to point out a DOE partnership we have with Volvo and a bunch of other great American manufacturers of Class 8 trucks is the Supertruck Initiative, one of my favorite names for an initiative. It had a goal of increasing the fuel economy of Class 8 trucks, 18-wheelers, by 50% within a few years. And I'm proud to say that just a few weeks ago, one of our partners validated that they've achieved at a full vehicle demonstration level a 75% improvement in fuel economy, basically that includes the amount of weight that you bring along with it. And that includes more efficient engines, bottoming cycles to get waste heat, some hybridization, having a pack of batteries so that the engine doesn't have to be on when the driver is sleeping overnight, aerodynamics, lightweight materials, tons of innovation. And some of that innovation is a little bit expensive now, and we'll get into the market a little bit later. But some of it, like the bottoming cycles, are going to be out in the market within the next couple of years. And so I think we're seeing a tremendous amount of innovation. Volvo and others are achieving great things that are showing that we can dramatically improve our efficiency of our Class 8 trucks.
I just want to add quickly that it's also the trailer itself is being integrated into that whole. Of course, trucks rarely go down without pulling something, so it's very necessary to include the trailer in the testing. And really a great program. It is creating new ideas and giving us the initiative to find solutions.
So one big global question, and then we can wrap up. Secretary Schultz has talked a couple of times about the need for an insurance policy when it comes to climate change. you know, we may not agree on the science, but just in case this is in fact a serious problem, we need to think about an insurance policy. His favorite is a revenue neutral carbon tax. Let's assume we put something in that actually put a price on carbon. What would it mean for these various transportation technologies? Would we see a veering off towards other fuels or other vehicles? What are the implications of a step like that? How do you think about it?
So I'll go first, and then others can chime in. The typical carbon price that you implement, if you're in the $25 to $50 range, it's such a small amount when you add it to the price of gasoline today that by itself it doesn't force the shift. The other thing I will say is some of these technologies that we've been talking about are already in the money. It's just a higher upfront cost either for the battery or for the fuel systems and the engine conversion. So they're not limited by economics today, they're limited mostly by these chicken or egg problems, or by how do we fit it into the existing infrastructure, how do we fit it into our driving patterns.
But presumably it has some impact on existing higher carbon fuels.
It would raise the price of existing carbon fuels, but not enough by itself to actually further accelerate the conversion. I think we have to actually focus on these infrastructure issues to get the transport sector to really move, and that'll have a bigger impact than the carbon price, which doesn't argue don't do the carbon price, it just says it's not sufficient.
You know, the way I look at it is, you know, I think you were involved in the McKinsey study around energy efficiency, which really showed, you know, what are the first greatest opportunities that come in for energy efficiency as the price of carbon goes up. You know, what are the opportunities that come into play over time? And I think we have a similar curve that we could generate around vehicle efficiency in transportation sector. And so what I think it would do is just really you'd have the same outcomes, but more quickly. So, you know, you get start-stop and hybridization getting in more quickly, electrification dialing up more quickly. You'd see fuel cells coming in more quickly. I think you'd see similar outcomes, but at a more accelerated time frame.
Yeah, it would be a small effect, as you said. In the case of synthetic fuels, you can kind of compensate for it by now reforming mixtures of methane and CO2, right? Or using some biomass at a small percentage, so you make up for the small change very easily by using those renewable components.
Just as a global company, we don't weigh in on these things. Right. We swim in whatever water that's put out there. So.
All righty. On that note, we've had a great performance by this orchestra, and let's give them a big round of applause.